Okay. Hi, so I'm Tom, and I will be presenting our work on, named Request and Conquer, Exposing Cross-Origin Resource Size. But before I dive into the details, I will first show a very simple example of, like a motivating example. So on the left, we have two users, so Mr. Bunzi and Lazy Lion, and both of them are part of the Twitter network. So they're logged into Twitter, and of course they send requests to Twitter. So for instance, if Mr. Bunzi wants to get a list of people that are following him, he can send a GET request to Twitter, to the followers endpoint, and he will include his cookies. Then Twitter will associate these cookies with the profile of Mr. Bunzi and will return the resource containing the followers of Mr. Bunzi. As Mr. Bunzi is a pretty popular guy, he has quite some followers, so the resource size is around 172 kilobytes. Of course, Lazy Lion can send exactly the same request, but with his own cookies. And again, there, Twitter will associate the cookies with the profile of the Lazy Lion and will return his followers. So in this case, around 44 kilobytes. So that's a very simple example. But of course, there's also attackers that can send requests to Twitter. So the attacker in this case can send a GET request to the profile of Mr. Bunzi, also getting his followers. And as the profile of Mr. Bunzi is public, Twitter will just reply with the followers of Mr. Bunzi, containing the exact same resource because, well, it's the same, the same followers that are included in this resource. Then the attacker can do the same for other users as well. So for the Lazy Lion, where he again gets the 44 kilobytes file back, and basically can start enumerating all the users on Twitter and getting the size of the resource. So then the attacker compiles a list of, or a table of usernames and associated resource sizes. And then this is the first step of the attack, and then in the second step is where the attacker first sets up some malicious JavaScript and injects it into a web page. So this JavaScript could be injected through like an ad network, or the attacker could actually own the malicious website, the website here that is then malicious. So now when Mr. Bunzi is browsing to the website, this website has no ID that this is Mr. Bunzi that's visiting the website. So that website has no ID that this user here is Mr. Bunzi on Twitter. So we can assume that for now, Mr. Bunzi is anonymous. Of course, when Mr. Bunzi is visiting the website, the JavaScript will also be executed. And this JavaScript can trigger requests to Twitter. So it will look exactly the same as in the first slide. So the exact same GET request with the cookies of Mr. Bunzi will be sent to Twitter. And because Twitter is unable to differentiate between this request and the previous one, it will send exactly the same resource again. Then the attacker can try to find out the resource size, so exposing the cross-origin resource size. And if he knows it, he can associate the resource size with an entry he found in his table, and then reveal the identity of Mr. Bunzi. Of course, it's important to note here that this can't just be done by default because well, we have the same origin policy which prevents the attacker from learning anything about resources that are not within his origin. So he should not be able to access the contents of this resource, neither should he be able to access the size of this resource. However, he can use certain attacks or size exposing techniques to still discover this resource size. So in our study, we set out to find techniques that can do this. So we analyzed all the operations that are performed on resources. So first, a resource is generated at the web server, then it will be sent by the host. It's transferred over the network, then it's received by the operating system of the client, and eventually it will be processed, and optionally it will be stored by the browser. And by doing this analysis, we discovered, or we found several attack techniques, so size exposing techniques. Many of these were found already, as you can see with the related work. But in this talk, I will mainly focus on the two new attacks that we discovered. So the one is traffic analysis on Wi-Fi networks, and the other one is side channel attacks against browser that leverages the storage mechanism. So I'll first zoom in on the Wi-Fi traffic analysis. So as you probably know, on WPA2 networks, all traffic is encrypted. And this means that also the TCP and IP headers are encrypted. So as a result, it becomes impossible to differentiate packets. It becomes impossible to know whether a packet belongs to background traffic or a target resource. And in order to still perform the attack, we propose to use a channel-based man-in-the-middle attack. So in this attack, the attacker clones the access point, but on a different channel, and then he prevents the connection between the correct access point and the client. So he basically acts as a man in the middle, and then he will selectively forward traffic coming to or from the access point. Visualize this looks as following. So you can see that the attacker is present in two cases. So he has set up this rogue access point and a malicious JavaScript file. So this malicious JavaScript file will send the requests to Twitter, as in the previous cases. So Mr. Bunzi will then encrypt the Wi-Fi packet and send it over to the attacker. The attacker will look at the size of this packet. Because there's no length hiding going on, he can know the exact size. And he will only forward this packet if it's part of if the length coincides with that of a TCP SYN or ACK, or of a TLS handshake. And that's required because Mr. Bunzi here needs to set up a TCP and TLS connection with Twitter. And he also forwards it if it's the size of the target HTTP request, because he wants to send the request to Twitter. And all the other traffic he blocks, and as a result, the background traffic, there won't be any traffic coming from Mr. Bunzi going outside, so the background traffic will die off. So if this packet is of one of these sizes, he will forward it to the access point, which will in return send it to Twitter. Twitter will then generate the response, send it back to the access point, which will forward it to the attacker, the rogue access point. And at that point, all the attacker has to do is subtract the overhead from the headers, so from the TCP IP headers and the Wi-Fi headers, and then again he gets the exact size of the resource, revealing the identity of Mr. Bonzi. So in a nutshell, that's how the Wi-Fi traffic analysis attack works. So now I'll move on to the side channel attack, leveraging the browser storage. So browsers, well, the modern browsers now have a cache API, which allows web developers to program the cache. So this means that any resource, including cross-origin ones, can be stored into the cache. And it's also important to note that the available space or the available amount of bytes that can be stored into the cache are limited per site. And because, well, mainly because of this, we discovered 3 different attack techniques that can be used to expose the exact size of a resource. So by abusing the per site quota, so the quota that's for every site, then the quota that's shared among every website, and then finally the quota management and storage APIs also can be abused to leak the size of a cross-origin resource. So I'll focus on the first one and the last one here, because the second one is basically an extension of the first one. So the per site quota attack looks as follows. So we have our user again visiting a malicious website. So for instance, hex.com. This could also be an iframe, so it doesn't necessarily need to be the website that he is visiting. So the first step that the attacker does is, with this malicious JavaScript, is completely fill up the cache, well, his own cache, so the cache of hex.com. After that, he will remove a certain amount of bytes. So let's say that he removes X bytes. And then in the second step, he will send a request to Twitter. Again, this exact same request. And Twitter will answer with a response. And this response, well, the attacker can determine that this response will be added to the cache of hex.com. So this fills up the cache with an unknown amount of bytes. And then in the last step, the attacker will again try to completely fill up the cache again, but now he notes exactly how many bytes are needed until he reaches the quota. So he can notice it, because then he will get an error saying that he can't store any more bytes in the cache. And well, as you can see already from the y and x, all the attacker has to do is subtract y from x, and again, get the exact size and reveal Mr. Bonzi's identity. Then for the second attack, which I think is a very good indication that, or serves as a good example, that when new APIs are introduced into the browser, they should be thoroughly checked, or at least at the security level. The quota management and storage APIs allow web developers to get some insight in the current usage of the cache. So what the attacker can do is he can ask for an estimate. So in this case, the cache was filled with X bytes. And although it's called getEstimate, the browser will actually return the exact amount of bytes. So at that point, the attacker knows that there are X bytes in his cache. And then he can again send trigger the request to Twitter, get a response, and put it in his cache. Now it grows to Y bytes. So again, you can send the getEstimate request, get a response back. Well, that all happens in the browser. So then the attacker knows that there are Y bytes. So now he just needs to subtract X from Y, and again, get the exact amount of bytes. So in these previous examples, I've mainly focused on a single attack scenario, namely the user identification by, for instance, using Twitter. But of course, these attacks can be applied in several other scenarios as well. So, for instance, if the victim is using an online health platform, such as WebMD, it may be possible for the attacker to reveal which medical conditions were entered by the user. In 2015, so last year, Gelerner et al. Proposed these cross-site search attacks, where the attacker simply sends requests to the search endpoint. So, for instance, with Gmail search, and by looking at the response size, you can determine whether this returned results or not. So, in their work, they used regular timing attacks, but of course, these attacks can also be applied by using the attacks that I just mentioned. And because there's a global cache that is shared among all websites, it's also possible to infer the caching operations of these other websites. So for instance, on the web client of Telegram, it's possible to detect whether a certain member is part of a group or not. And that's because if the victim is a member of this group, then Telegram will cache a certain resource which will affect the global quota. So this brings me to the demonstration. So in this demonstration, I will show how the identification on Twitter, so of a Twitter user, would work. So in a first step, the attacker will collect the resource sizes, as we saw in the beginning. So as you can see, here it collects information about users and my username as well. And you can see that this runs from the command line, so you can really distribute this easily among a lot of machines. And basically, it collects 3 different resources. So he collects the following lists and like resource, or at least the size thereof. And once he has a large enough list, he will say that this is his pre-computed data set, and we'll move on to the next step. So in the next step, the attacker either tricks the user in visiting his website, or the user visits the website by himself. As you can see, the attack already finished. So in this case, I really visualized everything that's going on, but of course, this is just JavaScript executing, so it could be executed without the user knowing about anything. So in this attack, the attacker will request 3 resources. So the twitter.com/following, the likes, and the lists will get the resource size by using the storage-based side channel attack. And then he will compare these resource sizes with what he found in his pre-calculated set. And then he will reveal the identity, in this case, me. Of course, we also looked at ways to defend against these attacks. One ideal solution would be to disable third-party cookies, because if these third-party cookies are not there, then the request sent by the victim will not contain any authentication. So the response will be unrelated to the identity of the victim. Unfortunately, by disabling third-party cookies, a small fraction of the web will break. So browser vendors are not so eager to disable them by default. A promising feature, however, is the same site attribute on cookies. So basically, this same site attribute says that, or mandates that if a cookie is sent from in a cross-origin, if a request is sent in a cross-origin manner, so if it originates from a different origin, then the cookie will not be attached. So by adding this attribute on your cookie, as you would with HTTP only or secure attributes, you can prevent these type of attacks. So for now, this mechanism is only supported by Chrome, but I think that other browser vendors will follow soon with implementing it. And we also looked at how the browser storage could be hardened. So for that, we proposed a solution where we add virtual padding. So with virtual padding, I mean that the padding is not actually written to the disk. It's only kept as part of some bookkeeping for the quota. And as a result, this will, the impact on the browser performance will be very limited. And 2 weeks ago, we learned that our proposed countermeasure will actually be adopted by browser vendors. So in Firefox, they said that it should be fixed in the next release. And then on the issue tracker of the storage standard, they mentioned that this should be a high priority fix, and that by applying it, the usefulness of the attack will be reduced of that of a standard timing attack. So that brings me to the conclusion. So in our work, we analyzed size exposing techniques. So we did an analysis on the actions that are performed on resources, which led us to the discovery of 2 new techniques, namely the Wi-Fi traffic analysis using a Wi-Fi man in the middle, and a second technique, namely the browser-based storage side channel. And both of these techniques can be used to determine the exact size of a cross-origin resource. And I have only touched on it briefly, but these attacks can be used in various real-world scenarios. And in the end, we also proposed certain defense methods, and some of them will be implemented by the browser. So if you're interested in knowing all the details, I suggest you take a look at our paper. I can assure you that at least my rabbit liked it.
Hi, I'm Rima Tanash from Rice University. So I have a question. You enumerated the users based on the resource size, from the GET request. How did you deal with collisions? Because when you start a new account, Twitter would ask you to have a minimum number of followers. Yeah. So you could have a lot of collisions. So how did you deal with that?
I'll show a different slide. So we did a more large-scale experiment where we analyzed 500,000 random users. And for each of them, we downloaded 5 resources. So the followers following likes and lists and memberships. And then we tried to determine the group size they belong to. So for instance, if there's a resource of the size 1, 2, 3, and we find that 3 users have this resource size, then the group size is 3. So you can see here, I think the most important one is by collecting all 5 resources, the group size is virtually, for most of them, it's 1. So that really reduces the possible set of victim users quite drastically. But of course, there are still some others. but of course, this attack is only targeting Twitter, but any social network or any website actually could be abused by trying to reveal more about a victim.
Hi, Antoine Lemay from Polytechnique. Just a follow-up question. Wouldn't that mean that you would need to sample essentially almost all Twitter users up to a refresh rate of the number of times somebody does a like?
Yeah, but you can use a more sophisticated attack where you reduce the size of the group size by having some offsets, basically. So if you basically not look at the exact size, but allow for a range, so that there could be small changes, then I think it could still be applied.
We have a couple of minutes left, so I get to ask a question. What can be done server side to detect or prevent this sort of attacks?
Well, at the server side, the best solution would be to add same-site cookies or the same-site attribute to cookies. Unfortunately, that will only prevent Chrome users from being attacked. All users on different browsers will still remain vulnerable because there it's not supported yet. But yeah, on the server side, it's quite hard to defend because from their perspective, the requests that are sent out from the attacker look exactly the same as those of a regular user.
All right, let's thank the speaker.